Hello, everyone. Our fifth speaker of the summer school is Professor Rahul Nandkishore from CU Boulder, and he will give us 3 lectures on many-body localization.
Do I need the microphone? Oh, you probably need it for recording. Okay, well, it's a pleasure to be back. I was, of course, a postdoc here, a few doors down. I also distinctly remember coming to this, earlier editions of this very summer school, taking the bus down from Boston, so it's doubly nice to be back here, but now sort of standing on the other side of the stage. Also to have a chance to tell you a little about many-body localization, which of course is a topic that originated with Phil Anderson, who's sitting in the audience. So, 3 lectures about many-body localization. In case you were wondering, this is Boulder, so this really is the view from my office, although I did not take this photograph. Okay, this is maybe a mile closer to the mountain from my office. And the brief outline of my 3 lectures is as follows. Today's lecture, or most of today's lecture, will be an introduction to many-body localization, essentially at the level of a colloquium. If you've heard a colloquium on many-body localization before, you've probably heard much of what will be in lecture 1. But I can't assume that you know that already, so I do have to do the basics. Then, after we're done with the colloquium, maybe even starting at the end of today's lecture, we'll start to talk about when you can many-body localize and when you cannot. And I'll introduce you to the general technique of locator expansions, introduced by Phil, which is the main analytic method by which people tackle localization. I will introduce various obstructions to locator expansion that people have identified. And I will also discuss ways around some of these obstructions. As part of this, I will also talk about localization and delocalization with long-range interactions, which is what Misha promised I would do earlier this morning. And then last lecture, probably tomorrow, I'll talk about how to go beyond locator expansions. And in particular, I will introduce to you the field of fractons, field in rapid development, and I will illustrate how ideas from the field of fractons may be used to open a new front in the battle against ergodicity. So with that out of the way, let's begin with our introduction. I do condensed matter physics, and this is the condensed matter summer school. Condensed matter, according to Phil, the basic idea is that more is different. And if you put lots of interacting degrees of freedom together, you can get completely new sorts of phenomena which have no real analog in few particle systems and cannot be deduced from first principles. And I would really characterize quantum condensed matter as the search for emergent quantum phenomena in many particle systems. And we have many examples of such quantum phenomena: superconductivity, Fermi liquids, magnetism. Really, over the past 50 years, we've had astonishing progress in equilibrium condensed matter. But I'm a young guy, you're all pretty young too. We should be thinking not about what we did in the past 50 years, but what's going to happen in the next 50 years. So in the next 50 years, what are the big open questions? Where are the big developments going to be? What will the condensed matter theory frontier look like in the year 2068? Okay, you can sit down and think about what the big open problems are. I highly encourage you to make your own list. This is mine. I think these are some of the important problems that are still open. It's not meant to be exhaustive by any means, but I think these are certainly open problems. Systems with strong interactions, systems with strong disorder, systems with both strong interactions and strong disorder, systems not at 0 temperatures, and above all, systems out of equilibrium. Equilibrium condensed matter, we understand a lot. Non-equilibrium systems, not so much. And the reason systems out of equilibrium are in italics is because the first 3 items on the list, I could imagine, and maybe these will be solved within our lifetimes. But I'm pretty confident that, barring breakthroughs on the immortality front, out of equilibrium will still have important open problems, no matter how long you live. So we then come to non-equilibrium quantum systems as the great open frontier for theoretical condensed matter physics. But one objection you could have about non-equilibrium quantum phenomena is, at least at first glance, it can seem like just a grab bag of random phenomena. There's this thing that happens here and this thing that happens somewhere else, and so on. Is there any unified theory paradigm for approaching non-equilibrium condensed matter? And if you feel like that, you should remember that in the year 1930, equilibrium condensed matter probably also seemed like a grab bag of random phenomena. There are all these different materials, they all behave differently. How do we possibly get any unified perspective in the whole field? Is it just butterfly collecting? And then there was Landau symmetry breaking and Fermi liquid theory and band theory and PCS theory, and all of a sudden the whole field starts to take shape as a coherent whole. And what we need is an analogous set of paradigms for thinking about non-equilibrium condensed matter. And the way I think about it, I think many-body localization is one such paradigm. Localization is one paradigm that helps make sense of this whole field of non-equilibrium condensed matter. And that's one of the reasons why it's interesting. As an added bonus, it also checks the other boxes. It involves systems which are strongly disordered, systems which are interacting, systems which are far from the ground state. It involves real-time dynamics. So really, it sort of checks all of my boxes in my list of what are the great open problems in condensed matter physics. So that's why I think it's interesting. What I'll do now is I'll tell you what many-body localization is, what it has taught us, and in particular I will highlight two stories, the story of localization-protected order, which will impinge also somewhat on what Misha talked about, and the story of emergent integrability, which will connect to what Marcos talked about. And then I'll talk about, outline some future directions still for the field before I dive into locator expansions and when you can and cannot localize. If there's questions at any point as I go on, please just stop me, put up your hand, ask. Okay, so what is many-body localization? At the risk of boring you with repetition, this is really a problem in the foundations of quantum statistical mechanics. In quantum stat mech, when you open up your textbook, you're told that you have a quantum system and it's coupled to some heat path with which it can exchange energy and particles, and that's why you can talk about canonical or grand canonical ensembles, and thanks to the coupling to the heat path, the system equilibrates at long times. And the process of equilibration and thermalization is associated with a loss of memory of the initial conditions. I could prepare the system in some very specific initial state, but once it's gone to equilibrium and is thermalized, all you can tell is what's the temperature, what's the pressure, what's the chemical potential, maybe some other number of Lagrange multipliers to do with the generalized Gibbs ensemble if it's integrable, but you cannot reconstruct all the information about the initial condition. Okay, so that's the usual setup for quantum stat mech, but there's a different sort of question which you could ask, and that's a question that pertains to the statistical mechanics of isolated many-particle quantum systems. So what I'm saying now is I have a single many-body quantum system in a box. It's not interacting with anything else. It's a closed quantum system. You can make the box as big as you like. It can surround your measuring apparatus, your entire laboratory. Right? All of those are governed by quantum mechanics. So at some stage, you should be able to model things as a closed quantum system. You have a closed quantum mechanical system. It's undergoing unitary time evolution according to its own many-particle Schrodinger equation. And now you're asking about the statistical mechanics of this. And this is a question that's actually now relevant for a number of ongoing experiments in cold atoms, trapped ions, cold circuits, NV centers, nuclear spins. The list goes on. It's also relevant for quantum information storage and computation. You have some assembly of qubits. What is the statistical mechanics of this system of qubits? So how can you think about time evolution in such a system? Well, the first objection you could have is that, well, maybe it should be impossible to thermalize in such a system, because we know that quantum mechanical time evolution is unitary, and that means it preserves information about the initial condition for all times. And you just told us that the process of thermalization was associated with a loss of memory of the initial condition. So there's some tension between that property and the unitarity of quantum mechanics. And of course, that's nonsense, because the information can be rendered inaccessible by hiding it in global operators. You have some information which is written to your initial state, and it's written into some local observables in your initial state. Now you have quantum mechanical time evolution, that information gets scrambled, and the only way to reconstruct it is to measure all the degrees of freedom in your system. And we can't measure Avogadro's number of degrees of freedom. The only measurements we have available to us are local measurements of few degrees of freedom. And if that's all that you have available to you, it could well be that the information about the initial condition, even though it is formally still present in the wave function, is now inaccessible to you. So what you observe will look like thermal equilibrium. So really the meaningful question to ask is, do accessible local measurements see thermal equilibrium at long times? And this leads to the notion of quantum thermalization in closed many-body quantum systems. So now the idea is that you have some subsystem A, the rest of the system B. You trace out all the degrees of freedom in B, and you get the reduced density matrix in A, and you ask if that looks like a thermal density matrix. And if it does, then any measurement made on A will appear to see thermal equilibrium. And this is really a question about whether B can act as a reservoir for A. Because if A can exchange energy and particles with B, then in effect A is coupled to a heat path, B being the heat path. If this is true, the system can act as a heat path for itself, and therefore it can thermalize. And there's strong numerical evidence that some isolated quantum systems do thermalize in this way. And now you could ask, well, do all initial conditions thermalize or only some? And of course, one special set of initial conditions for which we can do quantum dynamics is exact eigenstates. And this leads us to the eigenstate thermalization hypothesis, which I won't belabor because Marcos just spent 3 lectures talking about it. But the idea is that if you have a many-body quantum system which thermalizes for generic initial conditions, then it should also thermalize for eigenstate initial conditions. But eigenstates have trivial dynamics. So this must mean that the eigenstates are themselves already in thermal equilibrium, and therefore themselves constitute a good microcanonical ensemble for the problem. I'm hoping this is all familiar from Marcus's lectures. If you have questions, please ask. Okay. Not all systems thermalize. Integrable systems, which Marcos talked a lot about, are one well-known counterexample, but we don't know how robust integrability is. Could it be that if you have an integrable system and you perturb it, the property of not thermalizing goes away? Well, if that's so, then you would still say that thermalization is the generic behavior. But there is another class of systems which generically fail to thermalize and continue to fail to thermalize even for arbitrary local perturbations of the Hamiltonian. And those are the localized systems which Phil discovered in 1958. The basic, what happens in localized systems is that there's no internal reservoir. If I take the system and I partition it into B and A, then A cannot exchange energy and particles with B, so the system cannot act as a heat path for itself, and as a result, a memory of the initial conditions is preserved in local observables for infinite times. So I could write information to the initial condition, I could go away, and arbitrarily long time later, one of you could come along, measure the system, and extract an extensive amount of information about the initial condition. These systems, if you like, they're good stores of quantum information. They're good quantum memories. Okay, very brief history lesson. The idea of localization was first advanced by Phil in 1958. In fact, you go back and you look at his paper, and it's completely clear that what he's talking about is what we now call many-body localization, but for sociological reasons, which I don't understand because I wasn't around, people started to use the words Anderson localization to refer to single particle systems. Phil, do you know why that was? Then, in 1980, there was work by Flashman and Anderson, which demonstrated that localization is robust to lowest order in perturbation theory using locator expansions, which I'll talk about later in this talk. That result was extended to all orders in perturbation theory, summing up certain classes of diagrams by Pascal and Earl Schiller in 2006. They were working with a model like this, free fermions with disorder and weak contact interactions. Then there was a lot of numerical work by David Hughes over here and many others, mostly working with spin chains, and spin chains that look like this, a Heisenberg model with random field along one axis. And in 2014, John Imbrie actually presented a mathematical proof of many-body localization in generic interacting spin chain systems in one dimension. So now we really know that, look, the phenomenon is real, it can exist, robust to arbitrary perturbations, there's even a mathematical proof. And of course, there's hundreds of papers seeing it numerically in various different systems and also now experimentally. Brief summary of the differences between the thermal phase and the localized phases, both single particle localized and many-body localized. And the key point is that in the thermal phase, the memory of the initial conditions is hidden in global operators at long times. And in the localized phases, it's not hidden. It remains accessible in local measurements for infinite times. Question?
Whenever you say local, you mean real space local?
Real space local.
And you mean like exponentially decaying local? What's...
Right, so, and we'll see this later, yeah. So local, I mean up to tails in real space, which are typically exponential. If they were stretched exponential instead, I wouldn't sweat it. If they were even, power law, but a sufficiently high power such that most of the weight was in a compact region of real space, I would be happy calling that local also. So I never mean truly compact support. Okay. Yeah, so in the thermal phase, the eigenstate thermalization hypothesis is true. It's not true in the localized phase. The thermal phase could have non-zero DC conductivity. The localized phase does not. And there's various more detailed differences. For instance, the eigenstates in the thermal phase have volume law entanglement. There's ballistic spreading of entanglement. In the localized phases, the eigenstates only have area law entanglement. And the growth of entanglement is either absent in the non-interacting localized phases or it's logarithmic in time in the many-body localized phases. So, questions? No? Okay. So that's the key differences between thermalizing and localizing phases. The great thing about localized phases is they really constitute a new frontier for quantum statistical mechanics. The canonical and grand canonical ensembles are inapplicable. The system cannot exchange energy, or subsystems cannot exchange energy and particle number with other subsystems. Many of the traditional tools of many-body theory, which rely on the canonical or grand canonical ensemble, are also inapplicable. Many of the traditional theorems of StatMech, which make assumptions about thermalization, are also inapplicable. We now have access to systems like this in various platforms. And so really this is a new frontier for quantum StatMech. So now let me illustrate some of the new things that can happen in this new regime. And this is the story of new phases and phase transitions in the localized regime. And this is really work I did when I was a postdoc here. So it's, I guess, going full circle to be talking about it back in this room. Okay, so let's start by discussing symmetry breaking, since symmetry breaking is the most familiar example of phases of matter. Basic idea behind symmetry breaking, as we know very well, is that the state of a thermodynamically large system may not respect all the symmetries of the Hamiltonian. And the canonical example for illustrating this, always easiest to understand something by example, the canonical example is the transverse field Ising model. So that's a model with this Hamiltonian. It's a model of spin-half variables which live on the sites of a one-dimensional lattice. The Hamiltonian takes the following form. The sigmas are Pauli operators which act on the spins. There's a ZZ Ising coupling between nearest neighbors. There's a field that acts along the x-axis. And really the standard transverse field Ising model is just these two terms. But the experts in the audience will know that that's really an integrable model in disguise. You can do Jordan-Biggen transformation and it becomes free fermions. And I promised you I wasn't going to talk about integrable models. So I've added an extra term to the Hamiltonian. That's an x-x coupling. this spoils the integrability. Lambda is small. It's really just there to ensure that I'm not talking about an integrable model. Okay, so we know that the transverse field Ising model exhibits spontaneous symmetry breaking, and that's usually expressed as the ground state being a linear superposition of all spins up and all spins down with either a plus sign or a minus sign. What's the symmetry that's being broken? Anyone? What symmetry does the ground state break? Yeah, oh, Z2, but it's all spins flip, right? You take Z to minus Z, X stays X, Y to minus Y. That's the symmetry that's being broken. The Hamiltonian has the symmetry. These states do not. Now, spontaneous symmetry breaking is something that only makes sense in the thermodynamic limit. Any finite size system cannot break symmetry. And how do you diagnose spontaneous symmetry breaking? Well, there's various things you could do. So, for instance, what you could do is you could look at equal time correlation functions in the eigenstates. So you measure SZ here, SZ there, take one of the exact ground states, measure that correlation function, and that correlation function will have a long-range order out to distances of order system size. Or you could use a dynamical measure. You could measure SZ at time t equals 0, SZ at time t. You could prepare the system in an initial condition which explicitly breaks the symmetry. So you could prepare the system with all spins up, let's say. Now, the initial condition has broken symmetry, but the Hamiltonian does not. And you could ask if Hamiltonian time evolution restores that symmetry or not. And for the ground states of the Ising model, the energy splitting is exponentially small in system size. So if you prepared the system with all spins up, the uncertainty in that, or it would take the system exponentially long in system size to figure out that was not a ground state. And so that all spins up pattern would be stable to that time. And so if you measured the dynamical autocorrelation function, spin here at time 0, spin here at time t, that would have long-range order out to times exponentially long in system size. That would be another dynamical diagnostic for spontaneous symmetry breaking. Or you could apply an external field, and because the energy splitting between these two ground states is exponentially small in system size, an exponentially small external field would cause the system to polarize. Right? An exponentially small symmetry breaking field would cause the system to polarize, so it would have a huge susceptibility. So these are the standard equilibrium ground state diagnostics of spontaneous symmetry breaking. Yes? And by all of these diagnostics, the ground state of the transverse field Ising model breaks symmetry. We teach it in graduate courses, sometimes even in undergraduate courses. But it's in those same courses, we also teach that there is no spontaneous symmetry breaking in the transverse field Ising model away from the ground state. There are theorems about this. The relevant theorem is called the Landau-Peierls theorem. It's the discrete symmetry analog of the Mermin-Wagner theorem. So Mermin-Wagner says there's no spontaneous symmetry breaking of continuous symmetries at non-zero temperature in dimensions less than 2. Landau-Peierls says there's no spontaneous symmetry breaking of discrete symmetries at non-zero temperature in 1 dimension. Non-zero temperature means away from the ground state manifold. How does Landau-Peierls come about? Well, because if you consider the defects of the broken symmetry, those are domain walls. And the domain walls have some entropy. And at any non-zero temperature in 1 dimension, that entropy always overwhelms the energetic gain from aligning all the spins. And so you always prefer to have a disordered phase where the domain walls are running around all over the place. But entropy is an equilibrium concept. We're not in equilibrium here. So we can't talk about the entropy of the domain walls. And we really have to go back and re-examine the dynamics of the problem. So now we'll consider the exact same Hamiltonian that I showed you before for the transverse field Ising chain. But now what I've done is I've made the coefficients of this Hamiltonian random. Drawn from some distribution. Ground states look the same. But the excited states now also take the form of some spin pattern plus or minus its all spins flipped counterpart. And when I make it, so you could think about, let's say I switched off the h's and I switched off the lambdas and I just had this term, right? The ground state, well, now this kind of configuration is manifestly an eigenstate of the problem. This kind of configuration has a domain wall though. In the absence of disorder, the moment I turn the h's and the lambdas back on, the domain walls would start running around all over the place and they would destroy spontaneous symmetry breaking. If I was monitoring the dynamical autocorrelation function, for example, every time a domain wall crossed my spin would flip. And so even if I repaired an initial condition which broke the symmetry, the Hamiltonian dynamics would rapidly restore the symmetry. The motion of domain walls would scramble the magnetization of the spins, and they would no longer continue to be magnetized. But now, because I've made these coefficients random, having a domain wall here and a domain wall here does not cost the same energy. If I move the domain wall from here to here, or there, it changes the energy of the system. And energy is a conserved quantity in Hamiltonian dynamics. And if I'm in a localized phase, then there is no heat path from which I could borrow the energy. And that means the domain wall can't move. So now my domain walls are all localized on particular sites, because if they were to move, it would change the energy. And this means that if I were to prepare an initial magnetization pattern, that magnetization pattern cannot relax. I could repair the system with spins up here, down here, up here, down here. And because those domain walls cannot move, the spins are frozen in that configuration. And so if I measure the dynamical autocorrelation function, spin here at time 0, spin here at time t, that would now have long-range order. I could also measure the equal time correlation function in any eigenstate of the problem, and that would have long-range order in space. And these two cut states, this one with the plus sign and the minus sign, you can show they have an energy splitting, which is exponentially small in system size. So the susceptibility would be exponentially large in system size as well. So in fact, the excited states, even the highly excited states of this Hamiltonian, spontaneously break symmetry as diagnosed by all the standard diagnostics. This is not ferromagnetic type symmetry breaking, this is spin glass type symmetry breaking, but that's still spontaneous breaking of symmetry, far from the grand state manifold in one dimension, which is something that is supposed to be forbidden by the Landau-Parels theorem. But the Landau-Parels theorem uses this thing called entropy, which doesn't really make sense in the localized phase, and so we're not bound by the Landau-Parels constraints. Okay? So we can, in fact, get spontaneous symmetry breaking in highly excited states in one dimension, protected by localization. You could use this to encode information into your system. Of course, I gave you the example of the transverse field Ising chain, but you don't have to do Ising. You could do Z3, you could do clock, you could do various other discrete symmetries. Continuous symmetries are a different beast. I'll talk about those later. Questions? Hopefully that means it was all clear and not it was impenetrable. Okay, so we know symmetry breaking phases exist. Of course, anyone who's been looking at the archive in the past 10 years will know there's also something called topological order. So let's talk about topological order protected by localization. So topological order, of which quantum Hall effect is the most famous example, is a form of order which does not have any local order parameter, but instead is diagnosed through non-local quantities like Wilson loops or entanglement entropy or boundary modes. And in equilibrium, it's a property of ground states, and it needs a bulk gap. But in the localized phase, it can occur even in highly excited states, and no gap is necessary. And to illustrate how this works, again, it's easiest to do it by example. The cleanest example that I know of is the Kitaev P plus IP chain. So you have a P plus IP superconductor in one dimension. It has Majorana edge modes. And what you find is, so it has these Majorana edge modes when it's clean. Now, if you just look at the model Hamiltonian in Kitaev's paper, The Majoranas are there not just in the ground state, but in all the excited states as well. So now you may wonder, all these experimentalists working on Majorana nanowires, why are they working so hard to cool their system down to 0 temperature? And the answer is, well, Kitaev's model Hamiltonian is very special. It's a free fermion Hamiltonian. Experimental systems will not be free fermion. And if you have excitations in the bulk, and it's not a free fermion Hamiltonian, those excitations can mediate an interaction between the two ends. And if the two ends can talk to each other, then they're no longer truly Majorana. And what cooling to the ground state does for you is, in the ground state there are no excitations in the bulk, and so there's nothing which can mediate an interaction between the two ends. But if all you need is something which prevents excitations from mediating an interaction between the two ends, then you don't need the bulk to be gapped. It is enough for the bulk to be localized. Okay? So if you go into the localized phase in the bulk, such that the excitations in the bulk are all localized on disorder, then they cannot freely propagate and they cannot mediate an interaction between the two ends. And then you can have a phase with stable Majoranas in the absence of a gap in highly excited states, in this one-dimensional model. Again, I illustrated the idea for this simplest case of the Majorana chain, but it's true. It works also for more general examples. So you can consider Ising gauge theory, famous example of topological order in 2 dimensions, and you can show that you can use localization to get topological order in the Ising gauge theory in 2 dimensions at non-zero temperatures. Very recently, we also actually extended this to the Ising gauge theory in 3 dimensions, which is different because it has line-like excitations. But you can do a lot of topologically ordered things, also using localization. Now, if you introduce driving into the picture, that opens up a whole new universe of non-trivial phases, such as time crystals. Misha already talked about those, so I won't say anything more about time crystals here. But I do want to mention that you can't do literally everything with localization. So the most famous example of topological order is the quantum Hall effect, and we wrote this paper in 2014 where we claimed that there is no localization-protected version of the quantum Hall effect at non-zero temperatures. And we'll see exactly why later on when I get to the locator expansion section of my talk. So a lot of kinds of phases that are usually properties of ground states, a lot of kinds of order that are usually properties of ground states, can occur in highly excited states if you have localization, but not everything. What localization can do for you is it can preserve quantum coherence to high energy densities and thereby open up for you a new world of correlated high temperature phases of matter. Okay? So that's the quick preview of localization-protected order and what it does for you. The next story I want to briefly mention, which connects to what Marcus was talking about, is the story of emergent integrability. Here, I will just remind you that when you learn classical dynamics, and from whatever textbook you learn classical dynamics from, you learn that classical systems can be either integrable or chaotic. And then there's this thing called the Kolmogorov-Arnold-Moser theorem, which says, well, I've said integrability is robust to weak perturbations, but really what it says is that integrability goes away slowly. So in an integrable system, you have a huge number of constants of motion, you perturb the system, and some of them go away and others survive, and as you crank up the strength of the perturbation, they go away slowly. Quantum systems can also be either integrable or chaotic, but we do not know yet if there is any analog of the quantum KAM theorem and whether integrability survives generic perturbations. Many-body localization provides the beginning of an answer. What do I mean? Well, I mean that the many-body localized phase exhibits an emergent integrability, and what I mean by that is the following. Let us consider a system described by this Hamiltonian. So I'm talking spin half degrees of freedom on a line. The Hamiltonian is a nearest neighbor Heisenberg interaction plus a uniaxial random field. We know that for strong enough randomness in this field, this Hamiltonian goes into a many-body localized phase. where all of the eigenstates are many-body localized. And I claim that in this regime there exists a variable transformation which recasts the Hamiltonian into the following form. Looks complicated, involves many spin terms, but crucially this other Hamiltonian only involves tau z's, meaning that every tau z is a constant of the motion, commutes with the Hamiltonian, and additionally the tau z's and the s z's are related by some local unitary transformation, where again local means you're allowed to have exponential tails. And these coefficients are all local as well, and again local means you're allowed to have exponential tails. And if this is true, then it follows that this Hamiltonian secretly contains an extensive number of conserved quantities, of local conserved quantities, and that's all the tau z's. To give you some intuition for this, you could think about the non-interacting localized phase, characterized by some number of single particle wave functions. The occupation number of each of those single particle states is a constant of the motion in the non-interacting system. Now our claim is that you perturb the system, add in some interactions, and there's some dressed version of those constants of motion which continue to be constants of motion. If you perturb the system, then you retain this integrable structure. All that happens is you have some different dressing of the non-interacting integrals of motion. So the tau z's look different in terms of the s z's, but there's still an extensive number of tau operators. And therefore the emergent integrability structure survives. This notion of emergent integrability actually provides an extremely powerful way of thinking about many-body localization. You can understand a lot of the properties of many-body localized systems by thinking in terms of emergent integrability. I actually think maybe it's too powerful a way of thinking about many-body localization because people forget that you don't necessarily need all this structure to be localized, and we'll talk about that later. But the key point is that there exist many-body localized systems where there's an extensive number of constants of motion, and upon perturbing the system, the constants of motion may change, but the integrable structure survives. Okay, so just to summarize what I told you, my introduction to MBL, many-body localization is a new frontier for quantum statistical mechanics. It involves well-isolated quantum many-particle systems with strong quench disorder. Strong disorder is usually needed to get many-body localization, although it's an interesting open question of whether you can do without it. Key characteristic is that many-body localized systems do not act as heat baths for themselves. And in the localized phase, you can get new phases and phase transitions without equilibrium analogues, and also this rich kind of emergent integrability. Let me just highlight for you some of the future directions, one of which I'll be talking about, and the rest of which I won't be talking about in the rest of my lectures. Of course, there's lots of emerging experiments in many-body localization, including some from Misha, who was talking about them at the summer school. I won't be talking about those, but certainly making contact between the theory and experiments is an important ongoing direction. You could think about now relaxing the original constraint of having your system be completely closed and isolated. You could allow it to couple to an environment. How does that change the story? That's something we've thought a lot about. You could ask what new kinds of states can you get using many-body localization. So there was the two examples I gave you, the Ising chain and the Majorana chain, and we mentioned also time crystals, but there's more than that. We certainly haven't exhausted all the possibilities of new states which localization could give you. And this is also an important area of ongoing work. You could ask what can we learn more generally about integrability and the stability of integrability from many-body localization. You could ask whether you need disorder from many-body localization, because you could think that, well, if I have some interacting system of many particles, then each particle sees an effective potential which comes from interactions from all the other particles. And so if I have a translation invariant Hamiltonian, but I prepare a random initial condition, then if I prepare a random initial condition, then each particle will see a random potential, which comes from the random positions of all the other particles. And maybe this much randomness is enough to localize my system. So whether that really works or not is another important open problem. This scenario that I sketched for you is a lot like what happens in classical glass, by which I mean window glass. So you could ask if there's anything to be learned from many-body localization that could be applied to classical glass, or vice versa. You could ask, what can we learn about entanglement dynamics in general? And perhaps the very basic question you could ask, well, when can you have many-body localization, and when can you not? So that will be what I will be talking about next. Before I move on to the next section of my talk, I should thank various people who introduced me to the topic, with whom I did much of this work. And any questions? Yeah?
You said something about MBL stabilizing topological order
Yes?
in higher dimensions. But isn't the existence of MBL in higher dimensions still somewhat debated?
Okay. Up to that debate. So, there are arguments which I will discuss shortly, which say that maybe many-body localization does not really exist in higher dimensions. But what does this mean? And the content of the statement is maybe the localized phase is only stable up to some time, which could be very long. I think you typically get double exponential in the naively estimated localization length. If that is so, then yeah, strictly speaking, it's not truly an infinite time phenomenon. But double exponential in localization length could still be much longer than the lifetime of human civilization, and then maybe we don't care. So, and then the topological order would survive up to that lifetime. Okay, so that concludes the introduction. Let's start talking about locator expansions. I'm going to switch to Blackboard now. So I should say that what I'm going to be talking about, or my presentation of locator expansions, will be quite schematic. I will not attempt to be rigorous. Things can be made rigorous. You can introduce as many epsilons and deltas as you wish. If you want to see that done, I encourage you to go to the original papers. I'll give you the references. But I wouldn't attempt to do it here because I don't want to spend all 3 lectures talking about minutiae of locator expansions. I will instead try to give you the main ideas and the flavor for how the argument goes. So the basic idea of locator expansions, well, I think the reference for it is Anderson, 1958, classic paper. What I'm starting with is locator expansions for one particle systems. So let's start with locator for one particle systems. So let's consider a single electron in a random potential. So one electron in random potential. And for simplicity, let us consider for now a system that's on the lattice. So here's energy, here's position. Let me do one dimension for maximum simplicity. You could do it in higher dimensions if you wanted. It's not an essential distinction. I have some set of energy states. It's a random potential, so they have some distribution of energies. And the particle is sitting here, but it could hop. And let's say the hopping matrix element is T. So we have nearest neighbor hopping, NN for nearest neighbor hopping, T. And now we want to construct, let's say, the wave functions. Well, let's suppose, and let's say this typical distance between energy levels is of order delta E. delta E is the change in energy between two typical neighboring sites. And we want to operate in the regime where T is much, much less than delta E. And now we've got a problem because the electron moves over here and it changes the energy. And Hamiltonian dynamics conserves the energy. We could say that T gives some broadening to the energy levels. There's some energy uncertainty, but really that's only of order T, and T is much, much less than delta E. So in this limit, what you can do is you can construct, the electron can't move, because that would change the energy. Or it can only move as a virtual process. It can sort of hop and come back, because you're always allowed to do that in perturbation theory. And what that means is you can construct the wave functions in perturbation theory. So hops are virtual. And you can construct the wave function in perturbation theory. So let's say this site is x1, and let's say this site is x2, and so on. So your wave function psi, well, perturbation theory in what quantity? So it's perturbation theory in weak T. So in order T to the 0, the wave function is just particle sits on site x1. At first order in perturbation theory, there's some admixture of site 2. So at first order in perturbation theory, you get some admixture of site 2, and how much admixture? Well, T over delta E. Standard expression in second order in perturbation theory. At first order in perturbation theory. At second order in perturbation theory, you'll get some admixture of x3. And what will the weight be? It'll be something like T squared over delta E squared. Third order in perturbation theory, you'll get some x4 multiplied by T squared over delta T cubed over delta E cubed. Right? So plus dot dot dot. And as long as T over delta E is typically small compared to 1, each of these amplitudes will be smaller than the previous one. So the wave function will have very small weight a long way away. You could ask, how much weight does it have a distance r away? Well, if you want to get a distance r away, you have to go to order r in perturbation theory. That means you have to multiply by this small number r times. So the weight a distance r away will be this small number to the power r, meaning exponentially small in r. So the wave functions, they will have some amplitude arbitrarily far away, but that amplitude will fall off exponentially with distance. They'll be exponentially localized near the original position. So to get a distance r away, go to order r in perturbation theory. Can you still read as I'm writing down here at the back? No. Okay. Can you read this? Amplitude T over delta E r, which is approximately x minus r c. This is called the localization length. And from this expression, you can see straightforwardly that c is 1 over log delta E over t. And so if you were